Hello everyone. If you remember in the previous video we talked about model reference adaptive control or MRAC of first order linear systems, right? This is when we talked about this model here that was linear, first order time invariant, and we wanted the linear system to track this model, which is a similar structure. So the question is, what if it's a first order system but it's nonlinear? Could you still do it? And the answer is yes. Actually, it's a simple extension of that, and that's what I want to talk about in this video. So again, here the model is the same. The model is linear, but this time my system has a nonlinearity. Not only it has negative APY and BPU, it also has this nonlinear function, which is known function Fy multiplied by this coefficient Cp, negative Cp. So here I want my nonlinear first order system to follow the behavior of the linear model, which is first order. Okay? And the parameter AP is positive, AM and BM are positive. BM is just considered positive, it doesn't need to be, but AP and AM have to be positive in order for the systems to be stable. And here, if we want to, let's say for this, for this system, if we want to get a signal, a control signal, we can pick this signal assuming that all the parameters are known. If AP, BP, and CP, all of these parameters are known, then a simple control like this would do the job. So the first two terms are basically to make Y converge to YM, and this extra term is added to cancel this nonlinear term in Y dot. So if I plug in basically 7 in 5, I can see that, right? Let me do it. So let me write, if I plug in 5 and 7, you can see that Y dot, if you write it, the U, replace the U from 7 and reorder it, you're going to get this for Y dot. And now the three gains of your controller that you have, AR, AY, and AF. If you pick them as 9, guess what happens? If that's the case, AF becomes CP over BP. Okay, so this is CP over BP. So that BP and BP cancel, CP minus CP becomes 0. So that whole term will be eliminated. That's what I said. AR is BM over BP. So again, these two would cancel. You get BM times R, and then AY here times BP. This whole thing is negative AP or AP minus AM. So that whole thing is AP minus AM. And here the APs would cancel, and you get negative AM. So your control system equation becomes this. Y dot equals negative, there is a negative here, AM plus BMR, which is the same as 6, the original, the model equation, and that means your Y should go to YM. Okay, so if the parameters were known of the system, choosing control signal 7 and picking its parameters as 9 would guarantee convergence to error. But these parameters are not known. Remember, this is adaptive control. We don't know it. So what do? Instead of these three constant gains, AR, AY, and AF, we use estimates of them, AR hat, AF hat, and AY hat, where they are functions of time and they change. How do they change? We'll get to it. But we use this one. We use their estimates in the control law. If we do that and plug in 10 into 5, the governing equation for the control system becomes Y dot equals this. Here I did some factoring. And defining tracking error to be Y minus YM, and the error in estimation parameters as AR tilde to be A hat R minus AR, AY tilde to be a Y hat minus AY, and AF tilde to be a F hat minus Fy. If that's the case, where you subtract this equation 11, which is for Y dot, and what and 6, which is for ym dot, you get e dot on the left hand side, and on the right hand side you get all of this. Now here we add and subtract an extra am times y, and if you rearrange it, you'll see that your e dot becomes all of that. Okay, so here we did some rearrangement. Now this term here is your e, so it becomes negative am times e, which you can take it to the left side, so that's this guy here. If you look at here, remember that the definition that you had for ap minus am, this term here, if we go back and look, that is what, this is ap minus am, that is am minus ap. So that's going to be negative ay times bp, right? So that is negative ay times bp. Then the definition you have for bm, remember bm is ar times bp. So this guy is ar times bp. And for cp, if you look at the definition, that is af times bp. And if you look at these last three terms, they all share a bp in them, so we can factor them out. And once you factor it out, the remaining terms are going to be a y hat minus ay, a r hat minus ar, and a f hat minus af, which are the tildes. So it's going to be a r tilde r plus a y tilde y plus a f tilde f. So your governing equation becomes this. Or if you define p as the derivative operator, E is going to be bp over p plus am times this combined error term. So this is going to be your aerodynamics equation, equation 15. Now we pick the adaptation laws just like last time. Remember last time these were the adaptation laws, these two that we picked. So for the coefficient of the nonlinear function f, we also pick a very similar what? A very similar relation, negative sign of bp, gamma e, and this guy here is the derivative of e with respect to f, with respect to a tilde f, which is f. So this third equation is the new one that is added, and you can exactly show that if you pick your Lyapunov function to be this, which is, these are all the errors in the estimations, and this is the error in tracking. You can see that just like last time, this part I don't do all of the simplification. I want you as a practice to show that v dot still going to be negative ame squared, and your candidate function is positive, and your derivative, the derivative of that is negative. So that means your error is guaranteed to go to 0, and it will. The only thing is, will all of these tildes also go to 0? These guys, do they also go to 0 as well? The condition is similar. Your input R has to be what? Persistently exciting. If this R is persistently exciting, then the answer is yes, they will. If it's just a simple constant thing, not necessarily. Now, to show you the Simulink, this is very similar to last time, except now your system, as I said, has this nonlinear function. The function I chose is y squared, and the gain for it is 0.5. My model is still linear. Okay, so look what you're doing. You're making a nonlinear first order system with unknown parameters to follow the behavior of a linear system with the parameters that you decide. This is quite interesting, huh? That's a lot that you're achieving. And your adaptive control is the same. I just added this third branch here to do that f tilde, right? That's this last part here. It incorporates this equation for a f hat dot, and once you have a f hat, then you multiply it by f and add it to the other terms in u, and that is exactly what this third branch is doing. So this term here is what? This is a f hat times f, this is a y hat times y, this is a r hat times r, and that is u, and this is a f hat dot, which you can see that's negative of e gamma sine bp, which is this term, times f, which is that guy. And if you remember last time, the initial condition that I picked for these hats, you see, they are all starting at 0. So I have no idea what they are. Ideally, the values that they should be are what? If we go back and look at these formulas, let's take a look back. So what parameters do we have? This one, if you remember, was AP was 5, AM was 4, this BP was 2, this BM was BP was 2, BM was 3. In this case, CP for me is 0.5 and BP is 2. So the values that they should converge to is 1.5, half, and 0.25. Okay, and do they converge to these values? The answer is, since I use this harmonic function for my R, they will, if you look here. See that the yellow one, a R hat, is going to 0.5, the blue one, the Y hat, is going to 0.5 over time, 1.5, 0.5, and then the red one is a F hat goes to 0.25, and clearly the error in tracking is 0. As you can see, your system output does match what the model output. And if you want to give them meaningful names, call this YM, call this Y. So when you run it, it is giving you meaningful legends. Okay, here, look, there we go. And now if I switch to the constant input for R, let's see if I still get similar results. You know you shouldn't. Clearly your tracking error is still going to go to 0, but not these parameters. You see now this one does not converge to 1.5. It is about like 1.78. The blue one does not go to 0.5, only is about like 0.23 or something, and the red one doesn't go to 0.25. It's actually negative. It's like negative 0.1 or something. So none of my parameters are going to go to their actual values, right? The only thing that I will get is 0 tracking error. So this one is persistently exciting, this one is not. Okay, so I'm going to share the Simulink file for you, the download link under video description. Hopefully you can see now more of the power of MRAC, as now you can apply to nonlinear systems of first order. Next, I'm going to go to higher order linear systems, and then ultimately we go to higher order nonlinear systems like robots and so on. So you learn how to apply adaptive control to different systems. Thank you so much for your attention, and I will see you in the next video.